You think space has 3 dimensions because that's obvious. Left, right, forward, backward, up, down. 3 directions, 3 independent ways to move, and time is the 4th dimension. 3 space, 1 time. 4 total. Everyone knows this. But here's what nobody asks. Why 4? Why not 2? Why not 5? Why not 100? What determines the dimensionality of space-time? Is it fundamental? Arbitrary? Could it have been different? And if it could have been different, why is it 4? This is one of the deepest questions in physics. And the answer, or rather the answers, are strange. Some are mathematical, some are anthropic, some involve string theory and extra dimensions, and some suggest that 4 dimensions is the only possibility that allows complexity and life. I'm Leonard Susskind, and I've spent 50 years thinking about the structure of space-time, and I'm going to tell you why space-time has 4 dimensions. Not the simple answer, the actual physics, and why this might be the most important fact about our universe. Let me start with what we mean by dimensions. A dimension is an independent direction, an independent degree of freedom. In one dimension, you can only move forward or backward along a line. Position is specified by a single number. In 2 dimensions, you need 2 numbers. X and Y coordinates on a plane. You can move in 2 independent directions. In 3 dimensions, you need 3 numbers. X, Y, and Z. Height, width, depth. 3 independent spatial directions. And in 4-dimensional space-time, you need 4 numbers. 3 for spatial position and 1 for time. An event in space-time is specified by where and when it occurred. X, Y, Z, T. This is the structure of space-time according to special relativity. Space and time are not separate. They're unified into a single 4-dimensional manifold. Events are points in this manifold. World lines are curves tracing the paths of objects through space-time. And the geometry of this manifold, the way distances are measured, is given by the Minkowski metric. But why 4 dimensions? What would happen if space-time had a different number of dimensions? Let me tell you about the physics of different dimensions. Start with fewer dimensions. What if space-time had only 2 dimensions? 1 space, 1 time. This would be a 1-dimensional universe. A line. Particles could only move left or right. No up, no down, no forward, no backward. Just along the line. Could such a universe support complexity? Could it support life? No. And here's why. In 1 spatial dimension, you can't have crossing paths. If 2 particles are on a line and they move toward each other, they must collide or pass through each other. There's no way to go around. In 2 or 3 dimensions, particles can avoid each other. They can orbit, they can form complex structures, but not in 1 dimension. Everything is linear, sequential, no complexity. Also, waves behave differently in 1 dimension. The wave equation in 1 dimension has properties that prevent the kind of stable structures needed for complexity. Signals don't propagate cleanly. There's no notion of a localized disturbance traveling through space. 1 dimension is too restrictive. Nothing interesting happens. What about 2 spatial dimensions? 3-dimensional space-time total. 2 space, 1 time. This is more interesting. You could have a 2-dimensional universe, a plane. Particles could move in 2 directions. They could orbit each other. You could have collisions that aren't head-on, more complexity than 1 dimension, but still severe limitations. In 2 dimensions, gravity behaves strangely. The gravitational potential in 2 dimensions doesn't fall off with distance like it does in 3 dimensions. In 3 dimensions, gravity weakens as 1 over r. Move twice as far from a mass, the force drops to 1/4. But in 2 dimensions, the potential is logarithmic. It grows slowly with distance, but never vanishes. This creates problems. Orbital mechanics doesn't work the same way. Stable orbits are difficult. Planets couldn't orbit stars in stable configurations. Also, field theories in 2 spatial dimensions have different properties. Electromagnetism works, but the field lines can't spread out the way they do in 3 dimensions. The structure of forces is constrained, and most importantly, chemistry doesn't work. Atoms in 2 dimensions couldn't have the electron shell structure that gives rise to the periodic table. No complex chemistry, no molecules, no biochemistry, no life. Now let's go the other way. What if space-time had more than 4 dimensions? 5-dimensional space-time, 4 space, 1 time, or 6 dimensions, 5 space, 1 time. What happens? The first thing to notice is that gravity weakens faster with distance in higher dimensions. In 3 spatial dimensions, gravity falls as 1 over r squared. In 4 spatial dimensions, it falls as 1 over r cubed. In n dimensions, it falls as 1 over r to the n minus 1. This has profound consequences. In higher dimensions, gravity is weaker at long range. Orbital mechanics changes. The gravitational potential doesn't support stable orbits in the same way. In 3 dimensions, planets can orbit stars stably. The orbits are ellipses. They're stable against small perturbations. But in 4 or more spatial dimensions, the orbits are unstable. Small perturbations cause planets to spiral into their stars or fly off into space. There are no stable bound orbits. This means planetary systems, as we know them, couldn't exist in higher dimensions. No stable solar systems. No planets with stable conditions over billions of years. No time for life to evolve. Also, atoms behave differently in higher dimensions. The hydrogen atom, the simplest atom, has a ground state that's stable in 3 dimensions. But in 4 or more spatial dimensions, the ground state of hydrogen is unstable. Electrons would spiral into the nucleus. Atoms couldn't exist. No atoms means no chemistry. No chemistry means no life. This is a hard constraint. Higher dimensions preclude the kind of matter we know. Now, you might object, what about string theory? String theory requires 10 dimensions, 9 space, 1 time, or 11 dimensions in M theory. How do we reconcile this with the fact that we observe only 3 spatial dimensions? The answer string theory gives is compactification. The extra dimensions are curled up. Compactified. They exist, but they're so small we don't notice them. Imagine a garden hose. From far away, it looks like a 1-dimensional line. But zoom in and you see it's a 2-dimensional surface wrapped into a cylinder. 1 dimension is large and visible, the other is small and curled. String theory proposes that 6 of the 9 spatial dimensions are compactified into tiny shapes called Calabi-Yau manifolds. These are complex 6-dimensional spaces with special geometric properties. They're so small, about the Planck length, 10 to the minus 35 meters, that we can't detect them. We only see the 3 large spatial dimensions. This is mathematically elegant but raises questions. Why are 3 dimensions large and 6 small? What determines which dimensions compactify and which don't? String theory doesn't have a unique answer. There are many ways to compactify the string landscape. Different compactifications give different low-energy physics. Different particle masses, different forces, different constants, and we don't know which compactification describes our universe or why. This is the landscape problem. But the key point is that string theory is consistent with our observation of 3 spatial dimensions. The extra dimensions are there but hidden. Now let me tell you about the anthropic argument. This is controversial but compelling. The anthropic principle says that the properties of the universe must be compatible with the existence of observers. We observe a universe with 3 spatial dimensions because if it had a different number, we wouldn't exist to observe it. Universes with 2 or fewer spatial dimensions don't support complexity or life. Universes with 4 or more spatial dimensions don't have stable atoms or orbits. Only 3 spatial dimensions allow the chemistry and structure needed for life. So we necessarily find ourselves in a universe with 3 spatial dimensions. Not because 3 is special fundamentally, but because it's the only possibility that produces observers. This argument seems circular. We observe 3 dimensions because we exist, and we exist because there are 3 dimensions. But in the context of a multiverse, it makes sense. If there are many universes with different dimensionalities, most will be sterile, empty, lifeless. Only universes with 3 spatial dimensions will have observers. And those observers will ask why space-time has 3 spatial dimensions, and the answer is observer selection. We're here because this is the kind of universe where observers can exist. Now, this doesn't explain why the multiverse exists or why it explores different dimensionalities, but it does explain why we observe what we do. Some physicists hate the anthropic principle. They think it's giving up, that we should find a fundamental reason, a unique prediction from a theory. But if the landscape is real, if there are many possible universes, anthropic reasoning might be unavoidable. We might not be able to predict the dimensionality from first principles. We can only explain it through observer selection. I've gone back and forth on this over my career, but the more I learn, the more I think anthropic reasoning has a role, not as a substitute for physics, but as a complement. Let me tell you about the mathematical constraints. There are theorems in differential geometry and general relativity that constrain the dimensionality of space-time. In general relativity, the structure of space-time is determined by Einstein's field equations. These equations relate the curvature of space-time to the distribution of matter and energy. And the form of these equations depends on the dimensionality. In 2 dimensions, the equations are trivial. The Einstein tensor vanishes identically. There's no dynamical gravity. In 3 dimensions, 1 time, 2 space, gravity exists but has unusual properties. No gravitational waves. No propagating degrees of freedom. The gravitational field is completely determined by the matter distribution. No dynamics. In 4 dimensions, 1 time, 3 space, gravity is fully dynamical. Gravitational waves propagate. Black holes form. The equations are rich and complex. This is the dimensionality where general relativity is most interesting. In higher dimensions, gravity still works, but the behavior of waves and fields changes. The number of polarization states for gravitons increases. The structure of singularities changes. Black holes have different properties. Event horizons in higher dimensions are more complex. There's also a mathematical result called the hairy ball theorem. It says you can't comb a hairy ball flat without creating a cowlick. More formally, any continuous tangent vector field on an even dimensional sphere must vanish somewhere. This has implications for the topology of space-time. In odd spatial dimensions, certain topological structures are allowed that aren't in even dimensions. The dimensionality affects what kinds of fields and particles can exist, but none of these mathematical constraints uniquely picks out 3 spatial dimensions as necessary. They show that 3 dimensions is special in certain ways, but not that it's the only possibility. The strongest argument for 3 dimensions remains the anthropic one. Stable atoms, stable orbits, complex chemistry, all require 3 spatial dimensions. No more, no fewer. Now let me address time. Why is there only 1 time dimension? Could there be 2 times or 0? 0 time dimensions would be a static universe. No change, no dynamics, nothing happens. This is not a universe with observers. Observers require change, memory, causation. All of these require time. So 0 time dimensions is out. What about 2 time dimensions? This is more subtle. 2 time dimensions would mean 2 independent temporal directions. You could move forward or backward in 2 different time axes. Mathematically, this leads to problems. The metric signature would be different. Instead of 1 negative sign and 3 positive signs, you'd have 2 negative and 3 positive or some other combination. And this changes everything. In particular, the causal structure breaks down. In 4-dimensional space-time with one time, there's a clear notion of past and future. Light cones, causal ordering. Events are either time-like separated, space-like separated, or null separated. But with 2 times, this structure is different. The light cones are more complicated. Causality becomes ambiguous. You can have closed time-like curves more easily. Time travel paradoxes become generic, and the equations of physics become ill-posed. Solutions aren't unique. You can't predict the future from initial conditions. The universe becomes a causal, unpredictable, unstable. Most physicists think 2 time dimensions are physically inconsistent. The mathematics allows them formally, but they don't correspond to any viable physics. 1 time dimension seems necessary for a coherent causal universe. So we're left with 1 time, 3 space, 4 dimensions total. This seems to be the unique configuration that allows stable matter, chemistry, complex structures, and observers. Let me tell you about experimental tests. Could we detect extra dimensions? If they exist and are compactified, they're too small to see directly, but they might have indirect effects. Gravity could leak into the extra dimensions. At very short distances, near the Planck scale, gravity might become stronger than expected because it's spreading into extra dimensions. Experiments at the Large Hadron Collider have looked for deviations in gravitational or particle interactions that would signal extra dimensions. So far, nothing. The limits on the size of extra dimensions, if they exist, are very tight. They must be smaller than about 10 to the minus 19 meters, much smaller than we can probe directly. Another possibility is Kaluza-Klein particles. If there are compact extra dimensions, particles can have momentum in those dimensions. This momentum appears as mass in the large dimensions. You'd see a tower of particles, each heavier than the last, corresponding to different momentum modes in the extra dimension. These Kaluza-Klein excitations would appear at the LHC if the extra dimensions are large enough. But again, nothing has been seen. The universe looks resolutely 4-dimensional at all scales we can probe. Let me end with what 4 dimensions means for the universe. 4 dimensions is not arbitrary. It's constrained by physics and possibly selected by anthropic reasoning. Fewer dimensions don't allow complexity. More dimensions don't allow stable atoms and orbits. 4 dimensions is the sweet spot, the Goldilocks dimensionality, and this has profound implications. It means the structure of the universe, the number of dimensions is fine-tuned for complexity, for life, for observers. This could be coincidence, or it could be anthropic selection in a multiverse, or it could be that 4 dimensions is the only mathematically consistent possibility once you impose reasonable physical requirements. We don't know which, but what we do know is that 4 dimensions is special. It allows stable matter, chemistry, planetary systems, evolution, intelligence. It allows us, and that makes 4 dimensions the most important number in cosmology. After 50 years of studying space-time, I still find this remarkable. The dimensionality of space-time is not a detail. It's fundamental. It determines what kind of universe is possible, what kinds of structures can form, what kinds of observers can exist. And we live in the 1-dimensionality that makes all of this possible. 4 dimensions, 3 space, 1 time. The only configuration that allows the universe to know itself. Thank you for watching. Now you know why space-time has 4 dimensions. Welcome to dimensional physics.